Awesome. Thanks, Marissa. That was a great introduction. So as Marissa said, I'm Shannon Brown. I work at the Field Research Facility in Duck, North Carolina. I sit at the New York district, though, up in New Jersey. And today I'm going to be presenting on our satellite-based detection and tracking of inlet shoals. This workflow really tries to leverage the presence of whitewater to figure out the bathymetry in our inlet environments. I'm going to be presenting today on behalf of me and Ian Connery, who are co-PIs on this work unit, and some work done by Clay Caldwell, who is a smart student at Syracuse. So some great updates for you all today. I'm sure I don't really need to give much background or framing of this problem to you all, but just real quick, just try to frame the background of this work unit. So inlets are highly dynamic environments. You have an intersection of a lot of different forcings. You have tidal forcings and waves coming on the ocean side. And what you get is this pretty large ebb-tidal delta horseshoe type shape that stores a lot of sediment and can be kind of a sediment source for areas that need to stay free and navigable for our economy and stuff. So to get a good sense of how much sediment is in an inlet system, you need to go out and do a traditional survey. And with systems that are pretty large, that this could be pretty resource intensive, could take a lot of time to mow the lawn and then post-process that data. And our districts, they don't just have one inlet typically to maintain, and they have so they have a few, and we also have 13,000 miles of coastal waterways across the core that need to be maintained. So this is a lot of area to cover, and these areas are changing pretty rapidly. So it gets to be pretty resource prohibitive to get a now state of all of these systems and to have survey data that gives us a pretty good sense of how these systems are evolving and their current state. And what this often leads to in current day practice is emergency response dredging situations. This is a picture on the right of Manasquan Inlet, and this past summer, a hazardous shoal formed in the inlet throat, and you could see it being dredged, and it starts to impede the navigation way in Manasquan Inlet, and this makes us stop our plans and bring the dredge to a place that we didn't have it scheduled to be, and this can lead to higher cost dredging maintenance and also lower public perception. So what we're proposing in this work unit is to use satellites to start to gather more data. And this is Oregon Inlet in North Carolina, and it's a really great case study for our work unit because it has high wave energy. It's really dynamic because there's no terminal groins on either side. So there's a lot of sediment that's moving. And it's also a really big economic driver for the state of North Carolina and Dare County. There's a lot of commercial fisheries that go in and out of here. So there's a lot of seasoned mariners that are going in and out of this inlet, but it's still a pretty tough place to navigate. So there's some fatalities and it's pretty large, so it's pretty costly to maintain. So Oregon Inlet is kind of our poster child and what we'll be focusing a lot of this presentation on. But the reason for satellites is there's over 4,000 satellites in orbit as we speak. About 800 of them are Earth observing satellites, and they're satellites like Sentinel-2 that provide publicly available imagery, like you can see on the top right there. This is Oregon Inlet on a pretty high wave energy day, and you can see that it's really highlighting the ebb-tidal delta pretty well. It's all this white water. Here is following the shoal. And from an aerial view like this, you can pretty clearly see where waves are breaking and where might be your best path forward to get out of this inlet or even where the sediment is stored in the system. And you can see from maybe the perspective of a boat, it would be pretty treacherous to maintain. So we're hoping to leverage the power of satellites and hydrodynamic conditions at the time of image acquisition to start to estimate what the bathymetry is in inlet environments that have high wave energy days like this and start to get a sense of depth. So satellite-derived bathymetry is not a new concept. It's been around for a couple decades now in the 80s and 90s, and satellite-derived bathymetry can kind of be broken up into a couple different methodology buckets. But this work unit is kind of trying to fill two gaps in this type of research. One is that they're typically focused on nearshore borrowed environments or offshore, and this is going to be focused on inlet environments that have a lot of different challenges to work with. And then two, in things like multispectral analysis or using wave celerity to estimate bathymetry, these relationships kind of break down in whitewater conditions. So we are hoping to focus our workflow on producing bathymetry in these whitewater locations by assuming depth-induced wave breaking, to try to fill in those spatial gaps that we typically get with satellite-derived bathymetry. So this presentation, we have a couple different topics to go over. So I'm first going to talk about all of our different study sites real briefly that we picked for this type of workflow. Then we're going to go into kind of the nitty-gritty of creating a bathymetry product from satellite imagery. So this is called our short-term data product. We pull 4 months of satellite imagery and tried to create one bathymetry composite estimate. So we've been really working on optimizing that workflow, and I'm going to walk through all the progress we've made on that front. Then I'm going to real briefly talk about our long-term data products that we envision our tool to provide to our district end users, and then kind of give big picture updates. So as Marissa said, we're working with Alex and Justin, who are working on the multispectral side of the house. So ultimately, we want to integrate our workflow with theirs, and they're a bit further along. So we have some really exciting plots to show about how their interface is coming along and what kind of data products they'll show. Then we'll talk about some future research and conclusions, and hopefully have time for a little bit of discussion at the end. So this is a map showing all of our project sites that we've picked so far. The yellow ones are guaranteed project sites, and we've picked these in conversation and collaboration with Justin and Alex's team, as well as our district partners on our PDT. And so we've started to gather some data at these sites, and our goal really was to span different energy levels, so really prove when this type of workflow works and when we should pass the baton to Justin and Alex. And we've also picked different sites based on water clarity too, to see where things start to go wrong there as well. We have some potential sites that we haven't started working on yet, but picked in collaboration with the Detroit district and with good insight from Dan Buscone from Washington State. So these are all really interesting inlets with a lot of dynamic problems. But today we're really going to focus on Oregon Inlet, which is really our poster child for this workflow. It kind of has it all: high wave energy, relay dynamic area, and some good ground truth. So Oregon Inlet is a little bit south of the field research facility in North Carolina, and this is part of the Wilmington district. They have 6 surveys from 2022 to 2016 that we were able to get and compare to our satellite-derived bathymetry. You can see that they kind of span different spatial extent. Some of them capture a lot of the ebb tidal delta, and some of them are more focused on the navigation channel. But 6 surveys that we can compare to our satellite-derived bathymetry, so a pretty good amount, and different times of the year too, so we can start to test that wave condition component. So now I want to get into the nitty-gritty of the satellite-derived bathymetry workflow that we have been optimizing and evolving on. This is kind of a a broad look at the workflow, but really we can break it down into 3 main questions that we've tried to answer and optimize so that we can get the best bathymetry possible. The first one being, how do we get the best representation of whitewater pixels from satellite imagery? And that asks a couple different questions. What satellite images should we pull in? Should we pull in just Landsat and Sentinel, which are publicly available images, or should we include PlanetScope as well? And then should we classify the images with the COSAT classifier that's been published and is already available, or should we develop our own classifier that is really focused on picking out whitewater pixels and optimized for that signature? Then once we have the stack of classified images, how can we best convert those whitewater pixel locations and the hydrodynamic conditions at that time to a depth estimate? So that would be questions like, using this relationship, are we going to use a constant gamma, or are we going to have a gamma that varies based on the conditions at the time of image acquisition? And then what sorts of hydrodynamic conditions are we going to pull? This is supposed to be a tool at the end of the day, so we want it to be data that everybody has access to. So we're going to pull significant wave heights from WIS and wave periods from WIS, but that's offshore, so do we need to shoal it inward? So that's our question number 2. And then our third question is, what fusion methodology would create the best bathymetry surface from that 4-month time stack of satellite images? So right now we're just operating on a temporally weighted average, but there's obviously more sophisticated ways to do that. So that is question number 3. So we'll start out with answering our first question, which is, how do we get the best representation of whitewater pixels? So to dive into that, we started looking at our image sources. So Landsat and Sentinel-2, they are publicly available imagery, but they're a little bit coarser. They have spatial resolution ranging from 10 meters to 30 meters. And they have a revisit rate of 5 to 16 days, and those images go back to 1984. So that's a tremendous amount of data that we can work with, and there's a lot of existing pipelines that allow us to pull that imagery into our workflows. You can also see that this classified image over here does really nicely at picking out the whitewater pixels. So these are kind of our tried and true images, our Landsat and Sentinel. And then there's PlanetScope imagery, which is a commercially available product, but it is higher resolution. You can see when we zoom into this portion of the field research facility, it's got quite high spatial resolution for satellite images. It is about 3 to 4 meters for each of those pixels. But you can see that it does kind of underclassify the whitewater in this picture here. And that is coming to us at a temporal resolution of about 1 a day, and those images start in 2016. So a couple different data sources we can pull imagery from. We're going to really focus a lot of the presentation on using Landsat and Sentinel. Again, that's just our tried and true images, and hopefully we can start to work with PlanetScope a little bit more further down the line, and we have some results to show, but this is primarily what we'll focus on today. So coming up to our next question of what classifier should we use to pick out the whitewater pixels? Right off the bat, we just ran it through COSAT, which is a satellite-derived waterline algorithm that I'm sure a lot of you are familiar with, but it has a supervised classifier that labels each of the pixels in an image as sand, which you can see in these orange pixels, water in the blue pixels, and then whitewater in the light blue. And it could do this for the whole data set. So we ran it for 1984 to the present at Oregon Inlet, which you can see here, and these greenish pixels are going to be our whitewater pixels. And it does really well at classifying images pretty robustly, but I will say when when you do some comparisons, when you look at the OGB and then the classified image, it does tend to be conservative on classifying whitewater pixels and maybe just classify it as water instead. So that kind of got us down this rabbit hole of should we make our own classifier that really picks out whitewater pixels and starts to optimize that. So to start that type of analysis, we started a conversation with Dan Buscombe, who is really a part of this CoastTrain data set. And CoastTrain is a publicly available data set of labeled images. One of the very tedious parts of making a supervised classifier is that you need to label each of the images and tell them what the pixels should be classified as. So this is a great data set that's available online that has a lot of different classes that they have gone and labeled on each of those satellite images. And we thought by using this set of images, we could really emphasize the whitewater pixels in the classifier and be really good at doing that. So this is work that Clay really got into. So this was really a great type of analysis that we did. So he iterated on this a few times, but ended up with two models, two supervised classified models, this deep lab model and SegFormer, and then we have our COSAT, traditional COSAT classifier here, and this is all in Landsat imagery. And this is a lot of numbers to look at here, but I want you to look at this, the overall accuracy portion here, to show how well these classifiers did at labeling each of these images in each of these classes. So we still have the water, whitewater, sediment, and other classes. You can see that COSAT did better than these other two models that Clay developed. The models did outperform another satellite-derived waterline analysis tool called COSEG, but it didn't do better than COSAT. So we did this analysis on Landsat, and then we also did it with Sentinel-2 as well. And you can see a similar story. The COSAT supervised classifier actually did better. So we kind of put a hat on this type of the analysis, and we said, okay, the COSAT classifier is doing really well at classifying these images, so that's going to give us our best portion of whitewater pixels. Now, the next kind of sub-question in optimizing the whitewater pixel locations is to try to utilize different hydrodynamic conditions to highlight different parts of the ebb tidal delta. So if we just got one image and looked at the whitewater pixels, it might not give us a full picture of where the whole ebb tidal delta is and where the sediment is in the system, because there's only one significant wave height and the tide level as well. So we wanted to pull a range of satellite images and create a composite of that as well. So for each of the surveys here, we have 4-month time period, 2 months before, 2 months after the survey date, which you can see in the red line and in the text box there. And the satellite images that we're using in the composite are on the red dot. So you can see that by pulling 2 months before and after the survey, we're starting to get a range of significant wave height, a range of tide levels, and you can see that the tide levels are pretty spread too. So we're not getting any tide aliasing when we pull this extent of data too. Okay, so we've kind of answered our first question of how do we optimize the amount of whitewater pixels we're taking in. And now we're going to move on to the next portion of the workflow, which is to optimize the depth inversion. So we have significant wave height, we have water level. How do we convert that to bathymetry at those whitewater locations? So we wanted to see if we could optimize this depth-induced wave breaking relationship. And how we kind of started to do that is look at the literature and see what type of values the range of gamma is defined as, and this is kind of a whole can of worms. So it does get kind of complicated, but So there's this whole set of literature that really tries to define this relationship and give one constant value. But we wanted to start out pretty simple and use 0.78. It's pretty well accepted in the field. So if we use a constant gamma of 0.78 and take the WIS wave heights, can we produce bathymetry and compare it to the ground truth data? So that's the comparison I'm showing here. So we're taking the COSAT supervised classifier with our publicly available imagery. Again, that's Landsat and Sentinel-2, and we're using the WIS data. And here is kind of the area we're looking at where the ground truth data is. This first panel is showing the satellite-derived bathymetry. So taking 4 months of those satellite images and converting the significant wave heights to depth using the constant gamma of 0.78 and doing a temporally weighted average, we can get a varying bathymetry product. We can compare it to the ground truth survey that was collected in the middle of that 4-month period, and here's the surface difference in this third plot. And you can see it does pretty good. It has an RMSD of 0.67 meters and a bias of 5 centimeters. But again, we have a couple different surveys, so I'll show another comparison next. This ground truth survey was collected in April of 2022, and you can see that it doesn't capture the full tidal delta like the previous one did, but it still has a good amount of overlap with the satellite-derived bathymetry. When you look at the histogram of depth difference here, the RMSD is 0.73, but there's a really strong bias that the previous surface didn't have. So we can do this analysis across all 6 surveys, and on the top you're seeing the RMSD, and the bottom you're seeing the bias, and I mean, it's pretty impressive. The RMSD is all sub 1 meter, but sometimes we're getting really strong biases like 50 centimeters like we saw before. So our next question, our next thing to investigate was, where is this bias coming from? And our first thought was that it was because we were using WIS wave height, which is an offshore wave height. Should we shoal that wave height in and get a better representation of what the wave field was in the inlet environment? So just to give you a little bit of perspective, the WIS node is 18 kilometers offshore. So we wanted to see if we improved the RMSDs by shoaling that wave height in, and I think I saw Brad on the line, so I just want to say thank you to you. Ani Code sent me some code that I think has your name on it that shoals the wave heights in and can create a spatially varying wave height in the near shore. So here's just an example of taking a 1.2 meter offshore wave height from WIS and shoaling it in here, and we get a better representation of what the wave field might look like. And then we could do that same analysis, use 0.78 as the gamma, and see if that improves our RMSDs. And these orange plots now, orange bars, are going to show the RMSDs using that shoaled wave height. But it does not improve the RMSDs, and it actually makes the biases worse. So this was really interesting. We kind of went back to the drawing pad and said, what should we do next? But obviously there's a range of gammas in the literature. So we wanted to feed in a full range of gammas from 0.3 to 1.0 and see if there is an optimal gamma across the board for all of the ground truth comparisons that would give us the best bathymetry data. So using our Landsat imagery and our WIS waves, we fed in, again, 0.3 to 1.0 gammas into this relationship to see if we would get a consistently low RMSD across the board for 1 gamma. And obviously, seeing this figure, that didn't happen. We have 0.55 as the best RMSD, or so the best gamma for this April survey. And then we have a couple over here at 0.78, 0.8. So we didn't have a best gamma for all the surveys, which was a little tough to see, but okay, now we can also pass in the Shoals wave heights, and you can see the same thing. We are not seeing an optimal gamma that does the best across the board for all our different ground truth comparisons. So we went back to the drawing board again and thought maybe we need to have a varying gamma, but how would we calculate that gamma? So there's a couple of different papers that show relationships with your Barron number or beach slope or wave steepness. So there's a couple different paths you could go down to try to optimize this gamma. But since we have the ground truth data, we figured we'd calculate the optimal gamma for each of the satellite comparisons. So we would take our satellite image with our location of the whitewater pixels and feed it gammas 0.3 to 1.0 and see which gamma had the lowest RMSD for each of these satellite images. And then we can save the significant wave height, we can calculate the Barron number and the wave steepness, and see if there's a correlation with any of those variables to the optimal gamma. And real quickly, I'm just going to show how we calculate the Barron number and wave steepness, just so you can get on the same page. So the Barron number, we could get the offshore wave height from WIS. We calculated the offshore wavelength using the WIS period and the WIS significant wave height. The only thing we didn't really have is the offshore slope of the ebb shoal, and we found this relationship in the literature that we calculated. This is just a correlation between the annual significant wave height and the slope of the offshore edge of the ebb shoal. So that's how we calculated that and calculated the Barron number for each of those instances. And then pretty easily we can calculate the wave steepness. So for one of the comparisons now, we can get the best surface difference possible. So this surface difference here is showing at each of those images, we've used the optimal gamma, the gamma that will give us the best bathymetry data using WIS waves and our Landsat and Sentinel-2 imagery. The RMSD is pretty good. It's 66 centimeters with a really small bias. And then we could start to plot that gamma for each of those images against those different conditions. We have the wave height up here. Down on the bottom left, we have the optimal gamma versus the Barron number. And now on the bottom right, we have the optimal gamma versus wave steepness. And you can see that the strongest relationship is between the gamma and significant wave height. And it's pretty strong, R squared of 0.8. So we can do this for all of the surfaces, all 6 of those ground truth surfaces that we have. The histogram of differences, those surface differences are shown up here now and colored by the survey date. And then for each of the surveys, we have plotted, again, the gamma versus significant wave height, gamma versus Barron number, and gamma versus wave steepness, again, colored by the ground truth date. And across the board, we are seeing that there's the strongest relationship between gamma and the significant wave height. This is using WIS waves, and then if we show the WIS waves, we're actually seeing the same thing, seeing the strongest relationship between gamma and the significant wave height, and it's actually very similar, so it's scaling very nicely, 0.35 times the significant wave height plus 0.12, and then 0.36. So that was exciting to see. We can now use this relationship between significant wave height and gamma and recalculate our bathymetry composites and then RMSDs and see if this improves the RMSD and bias of our satellite-derived bathymetry. And that's what we're plotting here on this figure. So again, as a reminder, we're using Landsat and Sentinel imagery with our traditional COSAT classifier, WIS waves. Now we're calculating gamma using this relationship that we just defined and producing bathymetry and comparing it to our ground truth data set. So here the first plot is RMSD. You can see all of our surfaces are sub 1 meter RMSD, 0.8 meters to about 0.5. This second plot is the bias between the satellite-derived bathymetry and the ground truth data set, and it's much smaller than it was when we were using a constant gamma. If you remember, some of them had a bias of about 50 centimeters, and this one has a maximum of 15 centimeters, so we've reduced some of that bias. And this bottom plot is just the amount of images that's put into the composite in that 4-month period. Just an interesting thing to look at. So this is using Landsat and Sentinel-2 imagery. But remember, we have some planet scope imagery that we could start to work with as well. So these teal plots now are the planet scope imagery. And what's interesting is they are pretty consistently a little bit higher than the Landsat composites. They have a little bit higher bias as well. But if you look down here, they do have less images, so there's less data to work with, less hydrodynamic conditions that they're seeing to create the composite. And then this third blue bar chart now is showing you RMSDs, biases, and numbers of images if we use all of our resources, all of the images that we can. That's Landsat, Sentinel, and PlanetScope. And interestingly, it doesn't really change the RMSDs very much than just using Landsat. Obviously, we have a couple more images, so we're seeing a couple different conditions, and our biases are pretty good. So something to think about. Okay, the final portion of this workflow is the compositing methodology. And as I mentioned, we're doing a simple weighted average at the moment, but obviously there's more complex ways to create a composite of this data set. So this is something we're going to be working on in the future and exploring. So that was the detail of our short-term application, creating satellite-derived bathymetry at these whitewater locations. But again, we have a really large data set. So we have imagery from 1984 to the present, and we can really start to create some long-term decadal data products that could hopefully be useful for district engineers to manage their inlets. So we have a couple ideas, examples of what our long-term data products can be. And this is a whitewater probability map. So looking at full stack of data from 84 to the present, where are we seeing whitewater consistently? And that's what's shown up in this highlighted blue. You can see that the bar is highlighted. I mean, you can start to see the horseshoe develop. And then we could plot them colored by the date, and you can start to see if it's evolving, if it's moving around, and then look at the most recent day and see if there's any hazardous shoals that are forming. So those are kind of our ideas at the moment of long-term data products, but we'd love to hear if there would be any other metrics that we could create that you guys would be interested in. So as we've mentioned and Marissa mentioned, this is a work unit that's focused on high wave energy. And then there's another work unit led by Justin and Alex that is focused on days when there are no waves, when you can kind of see the sediment in the system and do a multispectral analysis. And they are really far along in their project. They have this really awesome tool in the works. And so you can see a couple different workflows that they're working on to pull out different bands. They're doing a blue-green band combination and DWI to start to see how the shoals are evolving on lower wave energy days. And I'll just point your attention down here to this transect in the Inlet throat in Barnegat Inlet, New Jersey. And if you plot multispectral and DWI over time, you can start to see how the shoal is moving north and south in the Inlet throat. So that is really interesting, and hopefully we can integrate our workflows after we get our workflow kind of nailed down, and give a one-stop shop kind of for inlet shoal tools. So I'll start to wrap up now. We have some goals for future research. So on our short-term application, we still kind of want to optimize the whitewater pixels that are going into our satellite-derived bathymetry workflow. So something that's really interesting is that boats that are pretty small can kind of make their way into the supervised classification whitewater pixels. You can see that in this Sentinel-2 image, you see boat wakes, and those actually get picked up in the classifier. So these are, you know, the deepest parts of the channel, and we are assigning it these shallow bathymetry depths. So these are causing some of our highest bathymetry estimations. So we are hoping to apply this machine learning algorithm that we just found, it was just published, that can go in and find boat wakes and hopefully mask them out to reduce some of that error. Another thing we need to work on is the compositing enhancement, like we talked about earlier, creating a more sophisticated way to fuse all those satellite images and create one bathymetry product. And hopefully we could then produce uncertainty as well, so we know when to trust the data and when not to. On our long-term application side, we would really love to take this whitewater evolution and create a course predictive model for any inlet that a district is working with, and kind of correlate that with some wave energy to see if we can predict when and where shoals are going to be. And then we're also open to feedback. We'd love to hear what type of long-term data products would be useful. And then to just conclude, to kind of give a summation, I've highlighted the workflow on the right that we found to be the most optimal so far. So we have seen that Landsat and Sentinel are kind of our tried and true image sources, and our COSAT classifier does really good. So using those two data products, we've made our classified images, and to transform them best into the bathymetry stack, we have found that WIS does just fine, and we created this relationship between significant wave height and gamma to create bathymetry from our hydrodynamic conditions. And then our composite bathymetry fusion methodology is to be determined, but right now the temporal weighted average is doing pretty good. But with that, I will open the floor. So thanks all for your attention, and hopefully we can have some good questions now.